Okay, so welcome to the Energy Symposium for Tuesday, April 26, 2022. I'm Dr. David Tuttle from the Energy Institute at the University of Texas at Austin. Our discussion today is environmental justice, climate change, air pollution, and decisions in the U.S. power sector with Dr. Inez Azevedo of Stanford. But before I introduce our speaker, let me give you a preview of the next UT Energy Symposium for the semester. It's on May 3rd. We'll have John Berger, CEO of Sonova Energy International, and he will discuss accelerating the energy transition. So with that, let me introduce our distinguished speaker today. She is Dr. Inez Azevedo, an associate professor in the Department of Energy Resources Engineering at Stanford University. She also serves as senior fellow for the Woods Institute for the Environment at Stanford University and a fellow for the Precourt Institute for Energy at Stanford. Professor Azevedo's research interests focus on how to transition to a sustainable, low carbon, affordable, and equitable energy system. She's interested in sustainability and energy issues where a systems approach is needed by combining engineering and technology analysis with economic and decision science approaches. Her current interest is to address energy issues with particular focus on distributional effects and equity. She has over 100 peer-reviewed journal papers and has participated as an author and committee member in several National Research Council reports from the U.S. National Academy of Sciences. She was one of the lead authors for the IPCC AR6 report on climate mitigation for the energy chapter, and she is now participating as a lead author for the upcoming U.S. National Climate Assessment chapter on climate change mitigation. Professor is also contributing as a chapter author to the upcoming U.S. National Climate Assessment report. She received the World Economic Forum's Young Scientist Under 40 Award in 2014 and the C3E Woman in Clean Energy Research Award in 2017, and we welcome her again to the symposium. It's great to have her here. After her presentation, she'll take questions. Please use the Q&A function and not the chat. And with that, we'll turn it over to Dr. Inez. And why don't you see if you can share the screen?
Can you see it now in presentation?
Yep. You're
wonderful. Okay, thank you so much, David, for this kind introduction. So indeed, it has been a pleasure, as mentioned by David, to participate in the IPCC AR6 efforts. I'll just note before moving on, that's not what I'll be presenting today. But for those of you interested in the topic, we also had editorial essay in the New York Times jointly with several other colleagues, John Beislein, Steve Davis, and Chris Bataille, on understanding what we should focus on in terms of efforts to address climate change mitigation and what sort of discussions maybe a little bit more of a waste of time and detracting for making actual progress. Happy to share the link later on for those of you that are interested. So today I'll be talking about issues related to environmental justice, climate, air pollution, and with a focus on the US power sector potential mitigation decision. Overall, the type of research that is performed by my group focuses on sustainable energy, what the engineering and economic feasibility for low carbon, sustainable, affordable, and socially just energy systems via both the efficient use and supply of energy. But of course, we won't move in this direction of hopefully low carbon and sustainable energy systems in a context where really policies and their design will shape the outcome and the design of the energy systems that we'll see in the future. So a second stream of research looks really at whether policies are achieving the intended goals in an efficient way, or if there are any sorts of unintended consequences from the designs of policy and regulations. And finally, we're making this transition to sustainable and low carbon energy systems with people that make decisions and choices and behaviors. So a third layer is really representing the people and the agents in the economy and how they may shape up the ultimate design and implications of the energy systems that we'll have in the future. For the last a couple of years, much of the emphasis on the work that my group has been pursuing focuses on quantifying environmental justice effects associated with energy decisions. I'm very fortunate to work with an extraordinary group of graduate students from different degree programs, and they are really the ones doing the hard work and having some really interesting ideas for us to study. So just showing over here the group of PhD students, mostly at Stanford, across programs of energy resources engineering, management science and engineering, civil environmental engineering, and the EASIUR program, which is a very interdisciplinary PhD program. And a couple of PhD students at Carnegie Mellon University that I'm still mentoring as they wrap up their PhDs. So let's start with the big picture and then zoom in. So the first thing that this crowd will know really well is that we need energy, but the benefits may come at climate, health, and environmental costs too, if some of the reliance for the energy that we use is based on fossil fuel. Two types of consequences associated with energy use: climate change and health damages from air pollution. And these two are particularly both and of this, such as CO2 and methane, and they have a global dispersion. They will stay a long time in the atmosphere. PM2.5 have a very different behavior. So first of all, the fuel combustion emits both directly PM2.5. This is called primary PM2.5, but also the emission of SO2, NOx, and this will react with ammonia in the atmosphere with the complicated equilibrium on what is the resulting concentration to form secondary PM2.5. Now, PM2.5 is associated with mortality rates, and so the overall health damages associated with PM2.5 exposure will depend on not only where the emissions occur, they will depend much more on where the concentration of PM2.5 will increase. Also, in contrast with greenhouse gases, the PM2.5 and criteria pollutants will have a short lifetime in the atmosphere. So really quite different behaviors here. Also, different sources of pollution will have different emissions compositions. So emissions from coal power plants out of very high stacks would emit primarily SO2 and NOx and have a wide dispersion. Industrial facilities dispersion. Then we'll have trucks to 5, as well as VOCs, which occur at the ground level and therefore with a much less dispersion than air pollutant emissions out of electricity generating units. So we and namely at University of Washington, led by a PhD student, at the time PhD student, now Dr. Manny Derntine, will electricity generation across the US. So here we're not looking at climate consequences, just air pollution and understanding its implications. And putting this in the scope of the environmental justice lenses. So first of all, in terms of big picture, PM 2.5 is the largest environmental health risk in globally. In the United States, with these values changing depending on the year the model used, and there is uncertainty associated with these numbers, but a fairly large number of annual premature mortality associated with PM 2.5. And electricity generation is still a significant contributor to this air pollution, namely associated with coal power, PM 2.5 levels has declined over time thanks to environmental regulations and the transition from coal to natural gas, largely driven by market prices, and thanks also to an increase in renewable electricity generation, though to a lesser extent than the contribution regulations and the transition from coal to natural gas. The literature reports a range between 10,000 and 52,000 premature deaths per year associated with the US electricity generation. But up until we did this deep dive, the demographic distribution of the resulting exposure was largely unknown. And so we estimated exposure to and health impacts from PM 2.5 from electricity generation in the US for 7 RTOs and from and to each state and by income and race. And so how are the marginal damages from air pollution computed, where there's several steps, and this sort of reduced complexity models have been developed by Chris Tesson, Julian Marshall in this portion of the work that I'm presenting. And what they do is first to have spatially resolved emissions data so that there is a good characterization of sources, not only electricity, but all sources. In first run of the model, all the emissions sources are considered, and the model estimates a baseline concentration of PM 2.5 for each location. Then following the baseline run, the model is run again, but now with the perturbation in emissions for every given source of emissions and pollutant type to compute the difference between PM 2.5 concentration that results everywhere from that marginal additional ton of pollutant. And then this is coupled with population data and an assumed dose response function, understanding on how an increase or decrease in PM 2.5 will affect mortality or decrease in the premature emissions. So in order to be able to run these models, we used InMAP, at the time calibrated to 2014, given that that was the most recent national emissions inventory, and used the annual emissions data for the major criteria pollutants. And then we coupled that with census data on self-reported race and ethnicity population by block group, as well as household.
Hey, Ines?
And results
Yeah, I'm getting some feedback that the audio is somewhat choppy. We could switch to where I'm displaying the slides and then you go to audio only mode and maybe that might help. You want to try that? Can you hear me?
I can hear you.
Okay. Do you want to share back to me and then I'll.
So
Let me do that. And just. Which slide do you see computing marginal damages?
no, we see the YouTube.
Okay. Let me change that. How about now?
So now we do see the PowerPoint presentation.
Yeah, it's the PDF for more reliability.
Oh,
And so
that's right.
if you
So,
just tell me when you want to change, I'll change the slides.
okay, and we see, okay, here we go. So I'm wondering if some of the figures will go away, given that I had animations. We'll check that out if need be. So, but in any case, if you move on to the next slide, please. So let's focus a little bit on the results from this modeling approach. A first result is that our own estimate of premature deaths attributable to electricity generation nationally is of about 16,700 premature deaths per year. So when we normalize that by the electricity generated in the US, we're talking about roughly 4 deaths per terawatt hour of electricity generated. From those, 85% are attributable to electricity generating units that are within the scope of an RTO. And 90% of the premature mortality is associated with coal electricity generating units. We also see key differences across the different RTOs. So we observe, so the table 1 on the left side provides the RTOs, their annual generation, and then the absolute number of premature mortality, as well as deaths per terawatt hour. And on the right side of the table, you see the generation by fuels and their share. In the figure on the right, you see the boundaries of the different RTOs, as well as just the share of coal in overall generation for the year of study. And so both MISO and PJM, which are very large markets and with still a substantial portion of the generation coming from coal, have the largest number of premature deaths that are induced by their generation. Whereas SPP also sees, though a smaller market, still sees also a high premature mortality intensity per terawatt hour of 6.7. Next slide, please.
Is this where some of the automation?
Yes, if you click again, let me just show if that shows up no. So I will need to share the screen, David, okay? But I will leave my video off. Can we do that?
Well, let's try. Go ahead and share your screen again for the
Okay, hopefully this goes well now without the video. Let me know if it's very choppy again in terms of sound. So here we're seeing the premature mortality per 100,000 people associated with electricity generating units PM 2.5 emissions. And across the United States, on average, we would see a premature mortality a little bit over 5 premature deaths per 100,000 people. We then look at how the premature mortality estimates are when considering race and ethnicity. And so what we see is that white, non-Latino. One could consider that this effect is associated also with income levels. So in this plot, we're showing premature mortality per 100,000 people by household income group. And so we do see that there is a slight decrease as income levels are higher, meaning people with higher incomes are generally living in their quality. But what we also see is that across all levels of income, the disparity between Black, African American, and the other groups persists. Now, there are also other issues that should be unpacked in this plot, because we're looking at this nationwide rather than in different regions. In the SI for this paper, we also included how the demographics and exposure and impacts would change from region to region. Moving on, and David, does it sound okay now, or is it just making sure that you can hear me okay?
Well, I'm getting chats that say that it's better, not too bad.
Not too bad.
Not too bad. So I think that turning off your video helped. And why don't we go through the animations, and then if it's still bad, they can chat back, and then I can start displaying it again.
Okay, apologies for that for all of you that are on that side listening in. I'll try to speak slowly also. Hopefully it's understandable and not too painful to hear with the choppiness of the sound. So here we're looking at another dimension, which is the different exposures parsed out by geography. So we're moving on to understand which states are responsible for premature mortality from electricity generation, and which states face the largest consequences from air pollution. So in this first plot A, we are showing the total deaths in each state from total PM 2.5 emissions from electricity in the entire United States. So this, putting it another way, is premature mortality that occurs between state boundaries, regardless of where the emission of the pollutant occurs. So it can be in adjacent states. And zooming in, we see that the states that face the largest premature mortality are Pennsylvania, Texas, and Ohio. Next, in this panel B, we're looking at the self-imposed damages. This means the premature mortality inside each state that is associated with emissions that also occur between state boundaries. And we see that a different picture emerges. For example, for Ohio and Pennsylvania, once again, the self-imposed damages from electricity generation between the state boundaries are much lower than what we've seen in panel A, meaning that a large portion of the premature deaths in those states occur due to emissions from other states. Now, in panel C, we showed the damage imposed to others. So we're looking at the premature deaths that a state is imposing on Ohio and Pennsylvania, that these states are imposing a high number of premature deaths elsewhere, not between the state boundaries. And finally, the net effect of looking at the self-imposed damages plus the damages to others minus the premature mortality that occurs between states. And I can call out over here the state of New York that in fact has amongst the top premature mortality, as we can see in panel A, that occurs between state boundaries, but where the self-imposed damages are fairly low, and where the damages to others is really on the very low end of this range, but they face on net the largest net imports of premature mortality associated with electricity and emissions from other states. So in summary, and I'll move on to a second portion of the talk, we find that the exposures are the highest for Black African American, followed by non-Latino white people. And the exposures for the remaining groups remain somehow lower. All of this is dependent on the grid mix that we'll have in different locations, as well as other factors, such as how our cities were designed. And the disparities by race and ethnicity are observed for each income level, indicated that those racial and ethnic differences hold even after accounting for differences in income. And the levels of disparity differ by state and RTO. And geographically, we observe a large difference between where electricity is generated and where people experience the resulting PM 2.5 consequences. 36 states have most of the health impacts attributable to emissions from other states. And most of the total impacts are attributable to coal rather than other fuels. I'll now move on to a piece that expands on some of these notions by looking once again at the US power sector, but thinking about what sort of transitions would we need as we meet climate and mitigation goals, as well as consider health benefits that may arise from transitioning to a more sustainable infrastructure. This was work done with several colleagues at different institutions, and with the lead author being my former student, Brian Sergi, who is now at NREL. And the rationale for our interest in this work is that climate policies often treat improvements in air quality as co-benefits from a climate policy. And despite the linkages between health and climate, few policies have been explicitly designed to optimize for improvements along both dimensions. The choice of which power plants are replaced by low emissions alternatives can dramatically alter the health benefits from a given reduction in system-wide emissions. So while there had been some previous work, up until that time, there had been a limited exploration of how spatially granular co-optimization of climate and health benefits would affect the emissions reductions across all US power plants. So we did just that. So the modeling approach is to explore how optimal locations for emissions reductions might change when we have a joint treatment of climate and health benefits in the objective function for the model. And we do so at the county level decision making. So overall, we developed a capacity retirement and expansion model to explore the implications of different locations when we think about just optimizing decisions for climate mitigation or for climate mitigation and air pollution jointly. So in the examples that you'll see in these results, we use the model to comply with a policy goal that specifies the need to meet the 30% CO2 emissions reduction target nationwide by minimizing social costs. And we compare the scenarios that optimize based on just minimizing climate damages plus investments in new infrastructure, or including also health damages from air pollution. A little bit more on that in just a couple of seconds. And we have some key assumptions. We assume that the capacity that is being retired is replaced by new capacity that is built in the same county, and thus eliminating the need for electricity transmission infrastructure. And so this abstracts us away from the real siting decisions, but provides some insight on some of the trade-offs that we'll see as we account for things like the capacity factors of wind and solar, specifically in each county, as we're looking for those replacements. David, please just chime in and let me know if something is not understandable. Otherwise, I'll keep going.
I think that you're doing fine. Thank you.
Thanks. So a little bit on data and assumptions. So we characterize the existing fleet of US power plants using SAM's database from the EPA, which includes hourly emissions and hourly generation for all fossil fuel units that are larger than 25 megawatts. This includes, in addition to the emissions and generation, also the fuel and unit type, the facility location, including coordinates. And then we model the GHG damages, the greenhouse gas emissions damages, assuming in our base case a social cost of carbon of $40 per metric ton of CO2. And we also consider the climate impacts associated with CO2, with methane leakage from the use of natural gas. That's not included in the objective function, but it is tracked in terms of the ultimate damages avoided or imposed as we select different types of strategies. And for that, we use the 100-year global warming potential. Now, for air pollutants, we do a similar treatment to what I described for the previous paper. So once again, we'll account for the emissions of the retired power plants and the substituted new infrastructure in the case of new plants that use fossil fuels, namely natural gas, as it is deployed. We compute changes in PM 2.5 and once again, the health damages associated with different options. And so we went over this previously. Given the uncertainty and ranges regarding the dose response function from air pollution, we use two response functions and contrast their values explicitly in the analysis. And the Harvard cities. And as the reduced form or reduced complexity models are also quite different, and there are at least 3 that are now quite used in literature. We to the air quality modeling, where AP3 a full chemical transport model, and InMAP has a modeling structure more similar to detailed chemical transport models, but simplified. We need to decide also what is the type and availability of new capacity to replace the existing infrastructure. As new infrastructure, either natural gas combined cycle plants, wind, or utility scale solar. For the natural gas plants, we assume that they are efficient and emitting just half CO2 and far less SO2 and NOx than coal, and thus resulting in fewer health consequences. And we assume that the NGCC plants would be dispatchable and meeting the same loads as the thermal loads that the coal power plants were providing. Natural gas combined cycle capacity with the same average emissions rates as those for recent units that came online between 2010 and 2017 from actual observed data in the SEMS database. And we assume specific capacity factors and heat rates relying on NREL database. We scale they meet the same annual electricity production as the plants that replace to account for methane upstream emissions. The other options of new infrastructure are wind and solar. And so for wind, we use site-level wind capacity factors from NREL, and for solar, also a similar strategy where we use the annually average horizontally radiance also from NREL, and then we downscale it to county level. We do make an important assumption, which is we do want to produce firm power to replace the retirements of the coal power plants. So the model is designed to require storage to be paired up with wind and solar. And you see the specs that we assumed for the storage costs. Now, moving on, how do you compute the costs of mitigation? So the total annual mitigation cost is defined as the additional costs of the optimization scenario relative to the baseline, where the baseline means operating the existing system. So it includes the annualized capital expenditures from all new capacity, as well as the sum of annual fixed operations, O&Ms, and fuel costs. And we subtract cost any savings from reduced O&M costs and reduced fuel costs that were paid to sustain the electricity production from the existing coal or natural gas plant that is being retired or reducing operations. For the cost estimates, we use NREL's ATB as data. In the results that we'll see, we use a 20-year useful lifetime and a 7% discount rate, and then we do a battery of sensitivity analysis in the SI. So we are developing a linear optimization model that is minimizing total costs, where the total costs include the TC, the costs of new infrastructure, as well as sustaining the costs for existing new capacity. And then we want to also minimize the social cost of carbon times the emissions of CO2. And in one of the versions of the modeling approach, we explicitly consider the health damages by including this factor W as 1, where we're multiplying the marginal damages by the emissions. G means the type of pollutant, the plant, and P the pollutant. So we'll account for both the pollutant types, SO2 and NOx, which would be the predominant causes of increase in PM2.5 concentration in the power sector. So I'll move on to some of the key results. Here in the vertical axis, I'm showing the annual damages in $1 billion. Under the baseline, meaning running the US electricity system as we're doing, and assuming a social cost of carbon of $40 per ton of CO2, we see an imposition on annual damages of a little bit under 70 billion per year. Now, that's just the climate damage. Looking at the air quality related damages on health, we see that depending on what concentration response function we use, we have ranges of premature mortality damages that may be even higher than the climate change damages, or lower, but in a similar sort of magnitude. I would note that the ACS function, which is the lower annual damages, is now the one that is most widely used as a benchmark dose response function, given that it pertains to a more recent study and with better controls on the cohorts and so on. We also see that there is a variation on the premature mortality damages, depending on the air quality model that we use. But the dose response function assumed is much more of an issue in terms of deriving very different results than the air quality model. Now, this is the baseline, meaning just using and operating the system as we do today. And now what happens when we impose a policy constraint where the CO2 emissions need to be reduced by 30% at the lowest possible cost in terms of building new infrastructure and retiring old infrastructure. So now we see that the emissions reductions are achieved. So emissions of CO2 are decreased by 30%, and thus the annual damages from CO2 are also decreased by 30%. And in that process, we have benefits in terms of reduced air pollution. And this simply because we're removing some plants that are higher, high carbon intensity that also happen to have a very high intensity in both emissions of SO2 and NOx, as well as resulting exposure and premature mortality. So there's some benefit there that arises from implementing this climate policy for the health damages too. So this is good news as this policy is imposed. But now, if we explicitly include in the objective function that we should minimize not only the total costs of new infrastructure and climate, but also the health damages, again, we meet the climate policy, that's our constraint, but we also achieve much lower health damages levels. This would just mean that the plants that we're retiring will be different under this scenario from the ones that we're selecting previously, as health damages are also explicitly included. Now, the question that you may have is, okay, but we're looking at minimizing costs and looking at the benefits, but what are the net benefits or net costs across these different types of selections? So that's what I'm showing in this next plot. So in the vertical axis, we have the annualized benefits in $1 billion. We're showing the results for the 3 different air quality models, and we can just zoom in on one since the insights are fairly similar across all of those. The orange bar represents the climate change benefits from this transition. So the annual benefits, assuming the social cost of carbon of $40 per ton of CO2. So depending on what social cost of carbon you like to assume in this modeling strategy, this orange bar would go up or down accordingly. The blue portion of this plot corresponds to the avoided health damages as we pursue this transition. And the green bars are the annualized costs of mitigation in terms of new infrastructure that needs to be built and operated when compared to the baseline infrastructure that we have today. So what you see as an outcome is that the black diamonds, which represents the net benefits, are positive, meaning if we look at this in the perspective of should we be internalizing this externalities from air pollution and climate change, and would there be a societal benefit by doing so? Yes, there would be one. So the benefits from air pollution and climate change are larger than the costs associated with building the new infrastructure. Now, what does the C and the H plus C bars represent? The C represents the situation where we're just minimizing the climate damages plus the infrastructure costs. And we track what happens to the health damages, but we are not minimizing those. And the H plus C represents health plus climate. And this is the situation where we are minimizing total cost plus climate damages plus the health damages from air pollution. And so importantly, we see, as we've seen previously, that we have larger annualized benefits when we move from the climate to the climate plus health strategies. And we also see that the net benefits actually increase when we do so by explicitly accounting for the health damages. And the costs of building this new infrastructure don't change dramatically. So they change by $1 billion across the scenarios. All of this is shown in terms of just illustration with bar plots and point estimates, but I would like to stress that there is, of course, uncertainty associated with all of these numbers. Here we're showing some of the resulting variation from the air quality model selected, but again, sensitivity analyses are warranted on assumptions for social cost of carbon, value of a statistical life, for health damages, and so on. Now, just as an illustration, here we show where the annual coal generation is in the baseline across the country. Those are the blue circles, where the annual health damages are incurred from electricity generating units in the sort of light beige to red underlying map. And then you can see that importantly, if we have only a climate policy and keep on tracking what happens to health, we have still maintain coal power plants in this region. Hopefully you can see my cursor. And on the climate plus air pollution policy, the types of coal power plants that are maintained are in different locations. And this is because some of these plants are really close to densely populated areas and then having high impacts to in terms of health damages. I'll move on to just a couple of more notes and I'll wrap up. But the first point being on just understanding some of these implications, again, under the environmental justice lens. This plot shows the median annual health benefits in terms of dollars per household as it is distributed by income quantiles. So from the lowest income quintile to the highest income quintile. And so we see that whether we account for climate only in the policy or health plus climate, so those two bars stack on top of each other for the second scenario, we have across the board annual health benefits for the different quintiles. And we also see that the lowest and second lowest quintiles are the ones that see a higher portion of annual health benefits, even more so when both health and climate are optimized together. So moving from, and I'll move to the next one. But in contrast to income, where we see a larger benefit towards the lower income households, when we display these results, again, vertical axis, median annual health benefits achieved, horizontal axis represents the minority quintile in a county. So the lowest minority quintile means there is very little minority as the share of the population in the county, to the highest minority contribution to the population in the county. And here we see that counties that have lower shares of minority population accrue the most health benefits per person, regardless of the optimization strategy that is performed. Now, finally, I'll just show that the generation capacity that is needed changes dramatically across states when we're thinking just about climate goals or health plus climate explicitly in our objective functions. The orange bars show a new capacity that would need to be installed in a state to meet just the climate goals. And the health plus damage objective function is shown in blue. So you see that in a state like Texas, for example, we move from a lot of capacity that would be retired to meet the 30% nationwide CO2 emissions reduction from a lower level of capacity that would be added when the air pollution consequences are taken into account. The diamonds represent the share of existing capacity that would need to be replaced in a state, and they are represented with the right axis rather than the left one. So I think I'm very close to be on time, if not surpassing the time. So just will reiterate some of the key messages, which are that even without including health benefits from reduced air pollution, a climate policy will bring substantial health benefits, making such policies a net beneficial from a societal standpoint. The range of health benefits here for a climate-only scenario are similar to the sort of magnitude of co-benefits that were seen in the Clean Power Plan and other proposed carbon reduction strategies for the power sector. However, by not including explicitly the health benefits from reduced air pollution and assessing them just after the fact as co-benefits, policymakers may risk to select drastically suboptimal policies from a society perspective. And so we show that the optimizations that include both health damages to be reduced, as well as climate damages and new infrastructure buildup, create quite a differentiated responsibility across US states from considering climate change alone. And so this really calls for the need for interstate cooperation across thinking on these infrastructure decisions in the future. Policymakers can also use the results that we've established here to help guide and mitigate disparities between benefits and the costs across different types of strategies across states and demographics as they think about designing air quality regulations, clean energy incentives, or subsidies. And although our analysis suggests that considering health would benefit lower income groups, this work and our previous work has shown that some race and ethnicities are disproportionately impacted by air pollution from the electricity sector. And so that ought to be considered in policy design. Thank you so much for your attention. Apologies if the sound wasn't great. I'll stop sharing the slides at this point.
Fantastic. Let's try to get some questions in. So on slide 40, it was interesting that you had a change between the climate only and the climate plus health in Texas. And can you unpack that a little bit more and describe what really transpired in the interplay there that made the requirement for new capacity go down with the climate plus health?
Yes, so I would think that a few things that come into play is that the generation in Texas is likely located in places that won't have as much of a dramatic air pollution consequences as some of the plants that are, for example, in the Midwest. And so as we pursue and a reminder that this is for just the 30% CO2 emissions goal. So the plants that would be prioritized to be retired would occur predominantly in other states. So that's the shift in the burden of replacement that you have as you include also health explicitly in the goals of the policy. Does that address your question? So that's the key driver.
Okay, so the location of the plants themselves versus population centers, I guess.
Mm-hmm.
Next question was, aren't fossil fuel power plants, coal and gas, under very strict air pollution regulations? How can these large emissions that are causing these health impacts be explained?
Yes, so that's quite right. They are under tight regulations. And so these are the emissions that we see both from the EPA emissions inventory as well as the national emissions inventory after such regulations have been set in place. So to put this in perspective, things were much worse in the past before we implemented FGD and other air pollution control technologies. So things are getting much better than they were 20 years ago in terms of the consequences from emissions from power plants. Things are even getting better also, as I mentioned at the beginning of the talk, given a transition from coal to natural gas, where natural gas is way less pollution intensive, yet this still contributes to premature mortality. Even with all the changes that were implemented, we still see that it is causing premature mortality in the range of over 16,000 premature deaths per year.
Mm-hmm. And then you've been doing this innovative work for a number of years, and through those years, there have been a lot of coal retirements. And so how has that really changed the dynamics? Or is there anything that stands out that you could point out with the retirements in coal plants?
Yes, indeed. So I would state that the levels of damages and thus also the benefits that are including here are declining over time owing to coal retirements and addition of the new infrastructure. So one of the projects that we have going on just now, we developed a sort of database, a dispatch model for US power plants that has been updated to 2019 fleet levels. And we're kind of updating much of this analysis as well as developing carbon abatement supply curves for decisions across the country with that updated data. So happy to share those results when they are out. But indeed, things are changing. And so in a lot of the dimensions that I'm talking about, we also do scenarios with future fleet of electricity generation through simulations and understanding how that will change in the future.
Okay, well, we're a little bit over, but let's get this one question in. The audience member thanks you for a very interesting and insightful presentation. And your study is focused on air quality. Do you think it's possible to use similar principles and methods to apply environmental justice to water quality? And how might it be different?
Oh, that's such a great question, but it's outside of my expertise. So I'll venture on this with the note that that's not my area of focus. I think for water quality, that's really there are such important questions, and it would be wonderful to have similar integrated assessment modeling exercises that occur. One of the things that I do see is that the data on air pollution is really something that is quite easy to use in United States applications, not globally, meaning really having the ability to have hourly emissions data for every single power plant in the United States that is larger than 25 megawatts is quite something. So I am not sure whether something even remotely similar is available in terms of water quality. The process is also in terms of modeling the consequences for water quality are probably quite difficult across different types of areas. So I'll end with that's I don't usually, I try to avoid saying it's a great question because everyone asks great questions, but this is definitely an area that should be of future research interests, to have a comprehensive way to address the implications of different infrastructure investments in the power sector. But I don't know how to do it. Maybe the person that asked the question does, which would be great to hear from.
Mm-hmm. And then let's try to slip in one more. So the question is, so retrofitting coal-fired power plants will have little impact in health benefits because the cumulative air pollution before regulations, or is there any kind of cumulative effect, or will retrofitting to improve their efficiency help that much?
So improving their efficiency may help a little, but not too much. Retrofitting coal power plants to operate with natural gas would make a very big difference. And actually, I don't think we consider that scenario. So when you're looking at the costs that we have over here, those would be really building new natural gas combined cycle plants. So yeah, I think I'll leave it at that.
Yeah, here's a clarification. Retrofitting with CO2 capture. So say you put CCS on a coal plant. Does that really help the PM 2.5?
Yeah, so that's that's a really good point. My understanding, not working as much on the CCS front, is that yes, that would actually help, as post-combustion CCS would require the flow to be cleaned up previous to the capture phase. So you would have some benefits there. I'm not sure how large those would be, but I think with post combustion capture, there will be some benefits to do so. Now, I think the way it will be hard to see this being picked up in the model given the cost of CCS. Not to say that under some scenarios of optimistic cost of retrofitting the plants, maybe that would be a selection. That's actually a good idea to explore more with this model. So thank you.
Thank you very much. with that, we're a little bit over, and thank you so much for your excellent presentation and your insights and your time.
Thank you so much for your time, and it's always a pleasure. Hopefully, one of the future years we'll do this in person.
Yes, we hope so again. Thank you again.